In section 5 of chapter 6, we want to look at some of the implications of the solutions of the Schrödinger equation for hydrogen atom, and this is going to lead to the concept of quantum numbers and orbitals. So let's start by defining orbitals. So when we solve the Schrödinger equation, solutions to the Schrödinger equation consist of pairs of numbers, which are the energies, allowed energies, along with the corresponding wave function that describes that energy. And as it turns out, for most systems, the hydrogen atom included, there are many different pairs that solve this equation, but each energy has associated with it a wave function. We call those wave functions that solve the Schrödinger wave equation for a one-electron system. Those are defined to be orbitals. That's what we mean by orbital. The wave function, this part, that solves the Schrödinger wave equation for a one-electron system. It's really important to understand that orbitals are different than orbits. They're based on the same word root, and they come from the same sort of etymological origin, but the meaning is very different. An orbital, remember, this is a wave function. It describes the probability for locating an electron in a region of space. Whereas an orbit gives a definite path followed by an electron, and that's not even a concept that's allowed in quantum mechanics because it violates the Heisenberg uncertainty principle. Let me just expand on that a little bit. The Heisenberg uncertainty principle, remember, says that you can't simultaneously measure, or know, if you like, the position of an electron and how fast it is moving. So if, for example, I tell you that the electron is located at this point, and it's moving in this direction, whoops, let me try that again. Let's see, there we go. Here, and it's moving in this direction. As soon as I move my pen, I violated the Heisenberg uncertainty principle because I've told you where it is and how fast it's moving at the same time. The very confusing conclusion is that electrons do not follow paths. They just don't do it. So that leads to some very confusing sort of properties of electrons that we'll see later on. All right, so these orbitals that are solutions of the hydrogen atom are described by three quantum numbers, n, l, and m sub l. I use a script L just so that you can tell the difference between my lowercase l and a 1. It's not super important that it is script, but it is super important that it is lowercase because uppercase L means something different in quantum mechanics. Okay? So every single possible valid combination of these three quantum numbers identifies an allowed state of the atom, by which we mean an orbital. So any possible combination of n, l, and m sub l that is allowable describes an orbital. And there's restrictions on the possible values of these numbers, and we're going to go over their restrictions and their meanings right now. So first of all, and this is important that it comes first because other quantum numbers depend on it, n is still called the principal quantum number, just like we did in the Bohr model. It has allowed values of positive integers, 1, 2, 3, 4, 5, 327, 1,032, 10,598. There's an infinite number of them, but happily we only have to deal with the first handful of them to describe atoms. The meaning of the principal quantum number is very similar to what it was for the Bohr model. As n gets bigger, the orbital size increases. That means you have to look in a larger region of space around the atom to have a reasonable chance of finding the electron. So the electron is on average further from the nucleus, and higher values of n give a higher value of the energy. Speaking of which, when we solve the Schrödinger model for the hydrogen atom, the energy that we get is this expression, which should be familiar because it is exactly equal to the energy equation for the hydrogen atom in the Bohr model, which is actually a good thing because we said that the Bohr model got the energy of the hydrogen atom spot on, so it's reassuring that the Schrödinger model also gets it correct. So now we're going to move on to the azimuthal quantum number, L. So this is the second quantum number. It's called the azimuthal quantum number. That has to do with the azimuthal angle around an atom. Another name for it is the orbital angular momentum quantum number. Its values are restricted by the value of n. So you have to know the value of n before you can consider the possible values of L. That's why it comes after specifying n. So notice, I'm just going to write here, and I'll do it again later, but there are n values allowed for L for the nth principal orbital number. So if n is 3, L could be 0, 1, or 2, and that's 3 different values. In terms of meaning, roughly speaking, the value of L determines the shape of the orbital, that is, the shape of the region of space around the nucleus in which you would have to search in order to find the electron. Now, we often replace the numerical values of L with a letter code using this sort of encoding table. If L is 0, we say it's an s orbital. If it's 1, it's a p orbital. 2 is a d orbital. 3 is an f orbital. And then it just goes roughly alphabetically after that, which leads some students to ask, well, why didn't they just do it alphabetically from the beginning and have it A, B, C? Well, historically, these letters were developed by spectroscopists who didn't know about the Schrödinger model yet. But in looking at the bright line emission spectra of different atoms, they noticed that some lines were particularly sharp, and they labeled them S lines. Other lines they labeled principal, or diffuse, or fundamental, and so it's sort of a historical development that led to this sort of odd ordering of the letters. It's just something you're going to have to remember because we do use these designations all the time. We'll use them next quarter. You'll see them used throughout the entire year of organic chemistry. It's just something you need to know about, especially the S, P, D, and F orbital designations. Finally, the third quantum number, m sub L, is called the magnetic quantum number. As the name suggests, it does have to do with magnetic properties of materials. The allowed values depend on the value of L, the azimuthal quantum number. So for a given L, m sub L can range from minus L up to positive L in unit increments. So for example, if L is 1, then m sub L can only be minus 1, 0, or 1. And just as I did previously, I'll just point out here, and I'll explain it later, there are 2L plus 1 possible values of m sub L for a given L. For example, as I just said, if L is 1, m sub L could be minus 1, 0, or 1, and that's 3 different values. Roughly speaking, and this is fairly rough, it describes the orientation of an orbital in space. So let's put this together and introduce a little bit more terminology. The term shell refers to the set of all possible orbitals in the hydrogen atom with the same value of n. Subshell refers to the set of orbitals with the same value of n and L, and these are usually designated with a value of n followed by a letter code for L. So for example, 1s subshell, the 3d subshell, the 5p subshell, etc. So if we apply these rules, we can build table 6.2 just from the fundamental rules governing quantum numbers. So if n is 1, L can only be 0 because L, remember, can only go up to n minus 1, which means that the only subshell in the n equals 1 shell is the 1s subshell. Since L is 0, m sub L can only be 0. So since each set of 3 quantum numbers describes a separate orbital, the 1, 0, 0 orbital, that's only one orbital in the subshell, and that means there's only one orbital in the entire shell. If n is 2, L could be 0 or L could be 1. There's 2 possibilities. If it's 0, it's called a 2s subshell. If it's 1, it's called a 2p subshell. If L is 0, m sub L can only be 0, so there's only one orbital in that level, subshell. But if L is 1, m sub L can be 1, 0, or minus 1, which leads to three different combinations of our quantum numbers, namely 2, 1, 1, 2, 1, 0, and 2, 1, minus 1, each one of which describes a separate, distinct orbital. So if we add 1 plus 3, we get 4 orbitals in this shell. And hopefully you can work out for yourself where the rest of this table comes from, following those sorts of principles. Now, I could ask questions like, how many orbitals are in the 5G subshell? Or how many orbitals are in the 5th shell? Let me just quickly go through how we can work out things like this. And there's some equations here, or some general guidelines that will help you do this very, very quickly if you can remember them. And that is, first of all, the nth shell has n subshells, namely L is 0, 1, 2, up to n minus 1, and that is n different values, each one of which gives you a different subshell. That's where the n subshells comes from. A subshell labeled with L has 2L plus 1 orbitals. I wrote this down a minute ago, but let me just write it out again. Remember, m sub L, if L is given, ranges from minus L plus 1, all the way up to minus 1, 0, 1, up to L. This set of negative values, there's L of them, namely minus 1 through minus L. There's L positive values, and there's 1, 0, L plus 1 plus L. That's where the 2L plus 1 comes from. Each different value of m sub L corresponds to a different orbital in that subshell. And finally, if we notice that the sum of the first odd numbers is m squared, so for example, the first three odd numbers, 1 plus 3 plus 5, is n squared, then we get the following rules. The nth shell has n squared orbitals, namely n squared equals 1 plus 3 plus 5 plus ... up to whatever the maximum number is. Let's see, so let's answer our questions up here. The 5th shell then has 5 squared equals 25 orbitals. How do I know that? Because of this number of orbitals in the nth shell. How about the 5G subshell? Well, let's see. I have to go through the letters myself. We think S, P, D, F, G. That's 1, 3, 5, 7, 9. They're just increasing odd numbers, so the answer is 9. Hopefully that shows you how to answer these questions.